Doing number 69, chlorinating solution to chlorinate a swimming pool. And so this is 7 parts of chlorine. Now, is that chlorine solution or pure chlorine? That's pure chlorine. So the substance chlorine. You know, remember substances are elements or compound, fixed composition. Pure chlorine, well, it doesn't, this is a little tricky because there are different chlorinating agents. But let's say whatever chlorinating agent we're using, there are going to be 7 parts of pure chlorine within that chlorinating agent. Per 100 parts of what?
Pool water?
Pool water? No. Not pool water. Yes. Of chlorinating solution. This is confusing because aren't they the same? Isn't chlorine the same thing as chlorinating solution? No. Chlorine's pure, fixed composition. Chlorinating solution is a mixture with variable composition. We could have higher concentrations of chlorine or lower concentrations of chlorine. But this is going to be 7 grams, or actually, I don't know, it just says by mass. If it's by mass, that means it could be 7 pounds of chlorine for every 100 pounds of chlorinating solution, or it could be 7 grams of chlorine per 100 grams of chlorinating solution, etc. I mean, we could use whatever we want here, but that's what a percentage is. It's part per 100, and this is by mass, so we just need any mass unit, and it'll work out. It could be tons, 7 tons of chlorine for every 100 tons of chlorinating solution. Whatever we want. Okay, next sentence. An ideal chlorine level for the pool is 1 part per million. Okay, 1 ppm. You guys remember part per million? Well, they're giving you a little hint to remember it. Think of 1 ppm as being 1 gram of chlorine per million grams of water. And so in other words, this is not the chlorinating solution, this is the pool water now. And so for the pool water, then we want to have 1 ppm chlorine. 1 ppm chlorine means 1 part of chlorine per million parts of total. Well, the total is just the pool water, right? Pool water. This is the same thing. The chlorinating solution is the total solution. And so we're going to have 1 part of pure chlorine per million parts of the mixture, pool water in this case. And so, you know, the parts are going to be by mass. This is ppm by mass here. And so we can just say 1 gram of chlorine, 1 gram pure chlorine atoms in a million grams of the mixture. And a million grams of the mixture would be pool water. Pool water is going to contain chlorine in it. And so this would be a ratio. We could flip it upside down or we could use it that way. It doesn't matter. You know, this would be read 1 gram of chlorine per million grams, or for every million grams of pool water, we'd have 1 gram of chlorine. You can just flip it upside down if you want. Okay, if you assume densities of 1.10 grams per milliliter, do you know what density is? Yeah, it's a mass to volume ratio. So different things have different densities. For example, the density of helium, you know, the density of helium is about 0.001 gram per milliliter, or 1 gram per liter. The density of water, of pure water, is around 1, not exactly 1, but around 1 gram per milliliter. The density of gold is 20 grams per milliliter. Gold is, you know, gold, iridium, platinum, those are all high density materials. And so this is more dense. Well, you expect the chlorinating solution or the chlorine solution to have a higher density because there's a lot of chlorine in there. You know, it's concentrated in that way. And so the chlorinating solution is going to have a density like that. Now, we need to be careful about the units. This is going to be 1.10 grams per milliliter. Now, grams of what? .10 grams of pure chlorine? Is that it? 1.10 grams of pure chlorine per milliliter of chlorinating solution? Yes? No. It's going to be 1.10 grams of chlorinating solution per milliliter of chlorinating solution. So for every milliliter of chlorinating solution, it's going to weigh 1.10 grams. Or, another way of doing this is we could do 1.10 grams per milliliter, and then outside the parentheses restrict this. This is just for chlorinating solution. Other things will have a different density. It's per 1 milliliter. And so this is the density of the chlorinating solution. The density of the swimming pool water, so I'll call this pool water, is 1.00 grams per milliliter. And so this is a different grams. So this 1.00 grams of what? This is only valid for pool water. It's going to be 1.00 grams of pool water per milliliter of pool water. And so we can do the same thing. So the numerator and the denominator are both the same thing. We'll just carry it outside. So 1.00 grams per milliliter, valid only for pool water. All right, so those are all the relationships that are given in the problem. What volume of the chlorine solution in liters is required to produce a chlorine level of 1 ppm in 18,000 gallon swimming pool? And so 18,000 gallons, that's fixed. We can't change that. These ratios we can double, of course. If we had 200 pounds, we need 14 pounds of chlorine, something like that. These ratios we can change as long as we maintain the same ratio. We're okay. However, 18,000, we can't double that because then we have 36,000 gallons full. We don't have that. And so we have 18,000 gallons of swimming pool water. 18,000 gallons of pool water. And then eventually I need to get to liters of chlorinating solution. But I have no idea how I'm going to get there. And so I'm just going to try to wind my way through this problem until I get to the answer. A dimensional analysis requires some patience because it's frustrating. But as long as you have some patience, you will make it to the end. So 18,000 gallons of pool water. We need something that gets rid of gallons or gallons of pool water. And so do we have anything that will get rid of gallons of pool water? That is, were we given any relationships that involve gallons of pool water? Like 1 gallon of pool water is equivalent to this. No. Grams and gallon, no. We don't. And so let's just get rid of gallons. Do we have a relationship that gets rid of gallons? Yeah. We could go to gallons to quarts, or gallons to pints, or gallons to cups, or gallons to ounces, or gallons to liters. Which one do you think we should do? Gallons. There are a lot of different paths, but let's try liters. We'll go from gallons to liters. This one is this one specific for pool water, or this one's for anything?
Essentially
anything. And so what is it? Well, in 1 gallon there's 3.785 liters. 3.785 liters in a gallon. Do I need that many sig figs? Well, it depends. It depends. Is this I have a blueprint of an 18,000 gallon swimming pool and I want to build, and so it's exactly 18,000 gallons in my plant, or is this an actual swimming pool? If this were an actual swimming pool and do you measure the amount of water in your swimming pool exactly? No. And so this would be probably to how many sig figs?
4.
Maybe 2 sig figs, 18,000 plus or minus 500 gallons or something like that. Maybe 2 sig figs. In that case, we're okay with 3 sig figs here. but we'll go with 4 since it's okay. It's not that difficult to use 4. So gallons cancel out gallons. So now I have liters of pool water. So if I'm interested in how many liters of pool water, I'm done. You know, so if this were converting gallons of pool water to liters of pool water, one step, it's over. But it's not. And so I need something that gets rid of liters or liters of pool water. Do I have anything that has liters of pool water? No. And so I'm going to just try to get rid of liters. And so I can go from liters to gallons, but if I go to liters to gallons, I'm going in circles, which often happens, you know, you're lost in the jungle. You can go in circles, but it's okay because you'll reverse and figure out the path. I don't want to go to liters to gallons. Where should I go? Liters to milliliters. I go liters to milliliters, so exactly 1,000 milliliters in a liter. And so liters of pool water canceled, that gives me milliliters of pool water. Now I want to get rid of milliliters or milliliters of pool water. Do I have something that gets rid of milliliters of pool water?
Centimeters cubed.
Yeah, I have something. I could go from milliliters to centimeters cubed. By definition, should I go that way? No, actually, if I have something that gets rid of milliliters of pool water, that would be nice. That would be better than getting rid of milliliters. And so where can I go? I have milliliters of pool water. I've seen that before.
1 gram of pool water.
Yes, not 1.00. There's going to be 1.00 because it's 3 sig figs. This is the way we read it. The way we read it is there's approximately 1.00 grams of pool water in exactly 1 milliliter of pool water. And so I go from milliliters of pool water to grams of pool water. Now, is there something that gets rid of grams of pool water and relates it to something else? Well, this is the density. I just used the density. Is there something else that relates grams of pool water?
The 1 gram of chlorine to 1 million.
Yes, yeah, exactly. There's 1 million grams of pool water, or actually, for every 1 million grams of pool water, I should have how many grams of chlorine?
1 gram.
1 gram of chlorine. And so now I got rid of grams of pool water and replaced it with grams of pure chlorine. Where am I getting all that chlorine? I'm going to get it from the chlorinating solution. In other words, I need something that gets rid of grams, or preferably grams of chlorine. And I got it. What gets rid of grams of chlorine?
1.10 grams of chlorine solution over 1. Oh, 1 milliliter of chlorine solution is equal to 1.1 grams of chlorine solution.
Is chlorine, pure chlorine, a mixture or element or compound, substance?
Pure chlorine
Yeah, it's a substance. It's a pure substance. Chlorine water or chlorinating solution is a mixture or a pure substance? Mixture. And so I cannot use 1.10 grams here. I cannot say 1.10 grams because that's not chlorine, that's chlorine solution. They aren't the same thing. This is why I say you have to pay high attention to detail, otherwise you're never going to get this. You're never going to get this answer because we need another one. What is it?
7.
Yeah. It's 7 grams of pure chlorine for every 100 grams of chlorine solution. So in this mixture of chlorine and water, for every 100 grams of chlorine water solution, I have 7 grams of pure chlorine in there. Does that make sense? And so now the grams of chlorine cancels out the grams of chlorine. Now I have how many grams of chlorinating solution I need. And so the next thing I need to do is I need to get rid of grams of chlorinating solution. Is there something that relates grams of chlorinating solution to something else? Yeah. 1.10 grams of chlorinating solution for every 1 milliliter. And so in exactly 1 milliliter is approximately 1.10 grams of chlorinating solution. This is only valid for chlorinating solution. And so grams of chlorinating solution cancels, and that leaves me with milliliters of chlorinating solution. Now I need something that gets rid of milliliters or milliliters of chlorinating solution. What should we do? Get rid of milliliters or milliliters of chlorinating solution? We should get rid of milliliters. And so if I get rid of milliliters, there are 1,000 milliliters in a liter. And so milliliters cancels, and that leaves me with liters of chlorinating solution. So this is liters of chlorinating solution, which is what I want. And so even though I didn't really have a path defined, predefined, or planned out, I just kind of, zigzagged my way through the jungle. So that's the dimensions. Now let's do the calculation of the numbers. Now the numbers, I'm going to go 18,000. You can follow along with the calculation. 18,000 times 3.785 times 1,000. I don't need to do times 1. Divided by 1 million. Times 100. Divided by 7. Divided by 1.1. I don't need the 1.10 because the O is not going to be factored into that. Divided by 1,000. So I always carry extra digits here, more than I'm allowed. How many am I allowed? Probably I'm allowed 2, looks like it. So it's 0.88. I'm going to carry extra, 0.8848 maybe. Let's carry 2 extra. And so if I were to round this would round to 0.88 liters. In other words, this is about 885 milliliters, roughly 885 milliliters. We're going to round it to 880 milliliters. Does that make sense? And so I need 0.88 liters. So if I dump this 0.88 liters into an 18,000 gallon swimming pool, then I should hit a chlorine level of 1 ppm. Correct? Yeah. All right, let me take a brief side trip to an advanced topic. The advanced topic is this. If I add this chlorinating solution to the swimming pool, is the swimming pool still 18,000 gallons? No. If I add the chlorinating solution to the swimming pool volume is going to go up. If the swimming pool volume goes up, we calculated the ppm for chlorine based on 18,000 gallons, but now we have more than 18,000 gallons. And so there's 2 ways of dealing with this. One way is we ignore it. We ignore it because is adding about a quart to 18,000 gallons, is that really going to change the volume by much? And so what we say is a negligible change in volume. So there's a negligible change in volume, it's not going to, it's wrong, but it's not going to be that wrong. If it's not that wrong, we're okay, we can live with it, right? However, let's say we don't have 7%. Let's say our chlorinating solution was really weak. We bought the cheap stuff. If we bought the cheap stuff and it's really weak, let's say rather than 7%, let's say our chlorinating solution were like 700 ppm chlorine. If our chlorinating solution were like 700 ppm chlorine, then we're going to be adding hundreds of gallons of chlorinating solution to our swimming pool. If we add hundreds of gallons, is that still negligible? No, that's going to be significant. And so this problem was designed in the way that it's pretty concentrated, this chlorinating solution, and therefore we don't have to add much. But if we did add much, then this is the wrong setup. And so I told you dimensional analysis is used for most problems, but there are some problems that we don't use dimensional analysis for. There are some problems where we have to use other methods. So what are some of the other methods we use? Some other methods we use are the two unknown methods. If we have two unknowns, right, then we need, in algebra, if you have two unknowns, you need two equations. Two equations, two unknowns. You've heard of that, right? System of equations. What are the two unknowns? The two unknowns are this. One unknown is what is the final volume of the swimming pool after we dump in all the chlorinating solution. The other unknown is how much chlorinating solution are we dumping in there? We don't know how much we're dumping in there. If we knew how much we were dumping in there, then we'd be able to know the volume. If we knew the volume, then we could calculate the ppm, right? But if we knew the volume, then we're already done with the problem, so we don't even have to do the problem. But it could work like this. So we don't know. So we're going to say this. We're going to have 18,000 gallons plus X gallons. The X is, however many liters of chlorinating solution, we'll convert that into gallons of chlorinating solution. And so this is going to be the chlorinating solution. Because the chlorinating solution is going to increase the volume of the swimming pool, and we want it at 1 ppm because right now it's going to be less than 1 ppm because of the extra volume. And then all these other ones are going to be the same. So we go 3.785 liters per gallon, and everything else is the same. Except at the end, what do we end up with? At the end, we should end up with, rather than going to liters, we're going to go to gallons. At the end, we want X gallons of chlorinating solution. And so what I did was I combined two equations and consolidated the unknown, so I only have one unknown now. This used to be an unknown, the total volume of the swimming pool after addition of chlorinating solution. But what I did was I substituted this in there from the other equation. The total volume of the swimming pool is 18,000 gallons plus whatever gallons of chlorinating solution I add to it. And so now I have one equation, one unknown, one equation, one unknown. I just solve for X. So actually getting the correct answer is not difficult as long as I know about two equation, two unknown. It's just a little bit more work, but we'd get the right answer. We wouldn't have this error, right? And so this is called two equation, two unknown. Two equation, two unknown we see in certain problems. Let me show you the type of problems we'll see it in here. So for example, if I look at number 76. What time do we go till today? 35. Okay. So I take a Fahrenheit and Celsius thermometer and stick it in the same object, whatever that is, or same solution, same whatever. It's in the same medium, immersed in the same medium. And so, like in the room, I could measure the Celsius and the Fahrenheit temperature of the room. Both. At what Celsius temperature will the numerical reading on the Fahrenheit thermometer be? 49. Okay. At what Celsius will the Fahrenheit reading be 49 degrees less than that on the Celsius thermometer? Or twice that on the Celsius thermometer? Or 1/8 that on the Celsius? Or 300 degrees more than on the Celsius temperature? And so let's take a look at B. Is there a temperature in Celsius here that the Fahrenheit will be twice what's shown on it? So for example, let's say it's on the Celsius, it's 20 degrees Celsius. The Fahrenheit will read 40 degrees Fahrenheit. Is there a temperature? Is there a temperature that the Celsius and the Fahrenheit will be exactly the same temperature?
0 degrees.
Not 0, because 0 degrees Celsius is 32 degrees Fahrenheit. Is there some other temperature?
0 Kelvin.
Actually, there is. Do you know what it is? You don't know what it is, but you can calculate it. You can calculate it if you know two unknowns because we don't know the Fahrenheit temperature, we don't know the Celsius temperature. All we need is two equations, two unknowns, and we can solve it. And so the first thing is, since I got a few more minutes left, is what is the relationship between Fahrenheit and Celsius? And so we're going to use the scientific method for this. The relationship between Celsius and Fahrenheit. Scientific method starts off with what? Observations. So we're looking at degrees Fahrenheit and degrees Celsius. And so my observations are like this. I'll set up a table, degrees C, degrees Fahrenheit. We'll put in some. At 0 degrees C, what is the Fahrenheit temperature? 32 degrees Fahrenheit. So water freezes at 0 degrees C, which is the same thing as 32 degrees Fahrenheit. At 100 degrees C, what is the Fahrenheit temperature? 212. Now, is it about 32 or exactly 32? Exactly. Is it about 212 or exactly 212? Exactly. These are exact. These are by definition. Did you know that? These are by definition. Well, scientists like to look for patterns. One of the patterns that we'll see is this. We'll graph it. We'll go from 0 to 100. This will be degrees C. So 0 degrees C. And then we'll go from 32 degrees Fahrenheit to 212 degrees Fahrenheit. This will be degrees Fahrenheit here. And so 0 and 32 match, 100 and 212 match. And this is a linear trend or a nonlinear trend. It turns out it's a linear trend. It's a straight line trend. That is, it doesn't curve. All of a sudden it becomes super high in Fahrenheit or super high in Celsius or vice versa. It's linear. Well, if I wanted to define this mathematically, come up with some kind of empirical equation. What's an empirical equation? A law, or what's another? What is it? Where does the origin of an empirical equation? From observation. It's a mathematical equation derived from observation. Well, my observation is this is a linear line. Y equals mx plus b. Y is the temperature in degrees Fahrenheit. M is the slope. So what is delta y? 212 minus 32 is 180 degrees Fahrenheit. Delta x is 100 minus 0 is going to be 100 degrees C. And so the slope is 180 degrees Fahrenheit over 100 degrees C. X is the temperature in degrees C. B is the intercept, which is 32 degrees Fahrenheit. And so this is the mathematical equation that, and this we call a law, right? This is the law of the relationship between Fahrenheit and Celsius. Now, oftentimes this is simplified in Chem 4 to degrees Fahrenheit is equal to 9/5 degrees C plus 32 degrees. Or 9/5 is simplified to 1.8 degrees C plus 32 degrees. So 9/5 or 1.8. Now, how many sig figs here? How many sig figs in 180? Infinite. That means in 100, infinite. 9/5 infinite, 1.8 is infinite. How many sig figs in 32? Infinite. All these are by definition. So the only thing limiting you is the how many sig figs you put in the variables here. Unfortunately, we're just about out of time, so I guess we'll do the examples next time. But we'll do some simple calculations, and then we'll do the two unknown calculations after that.